So I thought I'd do a harder example that has a lot more parameters and a lot more local variables. It's 5 local variables, so we can't even use our registers to store variables. It's not sustainable, right? We only have 5 registers. So how do we overcome this problem? Well, we can do things the way God intended and start using a stack to store our local variables instead of registers. Yeah, we can't get away with using registers to store one variable for the whole program because we need to use registers for intermediate calculations. So what we can do is we can allocate local variables when we're building up the stack. So first thing we're going to do is copy paste star, build up and tear down code. And we already have one local variable at R5 offset 0. That's already allocated for us just by the convention. Even if we don't use it, it's going to be there for you. But what if we wanted to add 4 more? Well, you really only have to change one line of code, and it's this line of code. Instead of adding R6 minus 5, we'll change that to minus 9 because we want 4 more. And now just like that, we have more slots for us. We have R5 minus 1, R5 minus 2, minus 3, R5 minus 4. So now I think we can start naming these slots. So I'm just going to make the arbitrary decision to name this one. Is going to be dedicated to AF. This one will be dedicated to BG. This will be CH, BI, BJ. And now that we have allocated spots in memory for these local variables, we can see how we no longer have the problem of running out of registers. It's a pretty common problem to run out of registers if you're trying to get away with using registers to store variables. But now, hopefully, this demonstration is going to help out more. So, go back to our body, and we'll just continue executing line by line as usual. Start with this one. So we're going to have to push A and F onto the stack. So I like to do it this way. There's many ways to do this, but I like to first move the pointer up 2, because we have 2 parameters, and then we need to make sure this first parameter is in the top of the stack. So first I'm going to load my A. Oh, and just to make it easy for me, I'm also going to have a table for all my parameters, so I don't have to count every time. The first parameter is always R5 plus 4, second is always R5 plus 5. So I need to get my A, load R0, R5, 4, it's my A. And I want the first parameter to be stored on top of the stack, so I'm going to store it at R6, offset 0. Offset 0 means top of the stack. The second parameter should be right below that. It should be the second most top thing in the stack before I call my JSR. So I'll load F, which I think is R5 plus 9. I'm going to store that right below my A. So this is to me this is a more intuitive way of storing things in the stack. We're still pushing it in reverse order, but the way we implement the code, the first parameter will have offset 0, the next parameter will have offset 1. Alright, that's the nice thing about this way, but you can do whatever you want. Just say so multiply, you can pop your value right off. Okay. And we'll have to move the pointer to its appropriate spot. We have to pop off our 2 arguments and our return value, so it's plus 3. And now we have to put this into AF. But since AF isn't being demonstrated by a register, it's being represented by a memory location. So what I can do is I can just store my R0 to R5 offset 0. Because that's the name for AF that we decided on. We decided it'd be at R5 offset 0. And that's really it. So now we don't have to worry about overriding AF because it's safe in memory. It can use all the registers. Now, next line of code. I shouldn't put here. So these are to separate my build material down. Okay, right there. Okay. Similar process. I'm gonna add move pointer up 2 to prepare these 2 parameters. I have to load B in there. R5. What's it? 5. Store B. Now I gotta get G in there. I think it's over here. R510. Store that. And then it's gonna be 1. Color JSR. It's pretty much identical top code. Load that back into register of choice, and then add 6. R6. 3 so it cleans up the stack pointer. And we're storing R0 in where? So we want to store it in BG. So what name do we pick for BG? Looks like we picked R5 minus 1, so I'll just store it right there. Okay. And we're done. Basically, the rest of it's pretty similar, so I'm just going to copy paste the rest of these lines. Well, I'm not going too fast for y'all, but it's because I'm just following this calling convention here. So it's not like I'm thinking about it. I'm just following the conventions. It's not like I'm using my brain to do this stuff. And yeah, let's just I guess we'll just copy paste it. It's very similar code, so I think C is located at 6. R5 is 6. H is located at R5 probably 11. And we're going to want to store it into our CH, which we named R5 minus 2. So instead of doing at R5 0, we'll store R5 minus 2. Very similar here. 7 and 12, I believe, and then minus 3. Here, R5 minus 4. E and J, is that 13? Yep. Alright, so yeah, you can see it's notice that we've only used 1 register this entire time. Like this is like we're not even close to running out of registers. Thanks to the stack, we can store this stuff in the stack. We don't have to worry about overriding it. And I've been able to use R0 for everything so far. So, alright, so now I'm done with these first lens code. I have to execute this one. So I'm gonna have to show you the power that I never lost AF, even though I've overridden R0 millions of times. AF is still safe exactly where I left it, R50. I'm just going to load R0, R50. This is AF now. AF. And then I'll have to use register 1 now because I need to add 2 things together, and those things need to be in their own registers. So unlucky we couldn't only use R0 for the rest of the program, but 2 registers is pretty good. You know, they give us 5, right? So, okay. Now I think R1 has VG. I'm just going to add them together. Oh, whoops. Yep. So now R0 has AF plus BG. And now I'm just going to load CH, which I think is into R1. I'll just keep the rest of them in R1 and just keep adding them to this R0. There's 0. R1. So now R0 should have AF plus BG plus CH. I didn't add them yet. Add R0, R0, R1. Now load the last in. Oops. I keep forgetting to add them. It's pretty funny. Alright. There we go. CH, STI, CJ. And great, so now we just return this answer at R0, so I'll just do what we always do. R0, R5, 3. And branch and tear down. In this case it's redundant, but it's always a good habit to store return values, just always branch and tear down. Okay, so that's our, looks scary, but I tried not to think about it that much. It's barrier go, I swear I put a barrier. Yeah. Oh, looks like it was here. Okay, but yep, so I was just doing things pretty zombie-like. I was just being like a human zombie, if that makes any sense. I just do line by line. It's like a factory worker. Okay, so now we're going to do multiply. And we're going to do the same philosophy of only using registers for intermediate calculations and not using it to store stuff. So, right, first, always, copy paste your build up tear down. And then just go line by line. So, oh, about the local variables. So, do I have to change this number? This -5? Well, not really, because we only need one local variable. And by default, there's always one allocated, so we don't have to change it. Just use a normal stack buildup. And we'll name the one spot we have given to us. We'll assign that to sum. And I guess we'll assign it parameters too, just to make it easier to follow. For B R5 offset 5. Okay. So we'll go line by line. Sum equals 0. I can do that by making any register I want a 0. And storing that into our sums location, which we decided is going to be here. Okay. Next line. We have a while loop. So before we evaluate the condition, we always want to just have a while label here. And then and while, and an unconditional branch back to our while. Okay. So now here we'll evaluate our condition. We have to get B. Thankfully it's already comparison to 0, so I don't have to do any subtraction. We'll just load B in. It's R5 plus 5. And then we branch to end while on 0. It's the opposite of not equal is equal, so branch 0 to end while. Okay. So now this is our body of our while loop. That starts out with an if statement. So we got B, and it's already a comparison to 0, so thankfully we don't do anything. So we'll just load B in. And I'm not trying to be clever. I already loaded B last line. I don't got to load again. I'm not trying to be clever. I'm just doing things line by line. That's what God intended, alright? So, right? Sum plus equals A. Oh, we'll have a branch to else. On the opposite of, what's the opposite of greater than is going to be less than or equal to? So, branch on less than or equal to. And then we'll have our else, end it. So I would like to do, when you're doing conditionals, I do the whole structure first, and then I'd implement the body. So that way you don't forget something. Here we'll want conditional branch to end if. That way the body of our if statement doesn't leak into the else. It's once it finishes, it's going to go directly to end if. Okay, so from here we'll start sum plus equals A. Our sum is in R5, so let's load the sum. It's more like, this is more like sum equals sum plus A. So I need to get sum plus A. R0. And R1 I'll load in A. Add them together. And I'll store this back into sum. R0, R5. I think sum is 0. Okay. Next line, minus B. There. I'll have to get B register. B is in plus 5. And I'm going to treat, interesting thing is, we have two local variables here, right? Now, local variables, they really aren't two parameters here. Now, and this is a local variable, but really, local variables aren't that much different from your parameters. They're kind of the same, right? They're both in the stack, and eventually they'll get torn down, right? The caller will, I guess we tear this one down, but the caller is going to eventually pop these off. So there really isn't too much difference between the two. We can treat them the same. So I'm just going to load B into register 0, subtract it by 1, I'll store it back. It's kind of weird we're storing it back into this parameter location, but it's perfectly fine. That is kind of what the code is telling us to do, right? B equals B minus minus. So we're just listening to our pseudocode. Okay. Now we're done with our body over if. Now go to body over else. Which is right here. So this line we'll get A in a register. I believe it's, or get sum in a register, because this is sum equals sum minus A. And we're going to need A in the other register. We're going to have to negate the A, to use complement style. Now we can add them together. Store it back. Store R0 back into our sum slot. So now we're done with this line of code. And keep going. Just line by line. I'm not thinking about what's above the line, what's below the line, just doing the line it's telling me to do. 5. Add it by 1. And it's really nice that I don't have to worry about overriding my registers. I've been using just R0. I have to think about, wait, what if I'm ruining some other important information by overriding R0? Well, all the important information is in memory. It's not in the registers, so don't have to worry at all. So str, we'll store that back into B. Done with B++. Okay, so this is the end of else. Looks like it's end the while. So yeah, we're done. Now we just got to go outside the while and do return sum. And so if the sum is in R0, so we'll load it into one register. And then we'll store that in our dedicated return zone, which is R5 plus 3, as always. You can always branch your teardown once you're done. And yeah, that should be it. So let's see if this works in Complx. Oh, also, just notice, this entire program, thanks to this memory, I only have to use R0 and R1, right? I'm given 5 registers to do calculations as R0 to R4, and I really only need 2. I've used only R0 and R1. And all the important stuff, all the variables, it's all in memory. It's not the registers. So this is probably, it's the most foolproof way to, although it's not the fastest, it's definitely the most foolproof way, because you don't have to worry about your old registers. And I think this is the way Professor wants you all to do it. So anyway, alright, let's go to Complx now. Okay, so I just loaded Complx. And it's like I had an error. My code's duplicate simple teardown. Let me actually change that. So it's because I have 2 teardowns in the same file. I'm just going to call this teardown 2 now. Hopefully that fixes it. Okay, so and I'm going to click on simulate subroutine call. I guess just do random and a matrix. I don't know, 5, 4, 3, 2, 1. Okay, and I'd want to see the stack, so I'm going to click on new view and adjust it a little bit. Okay. I'm gonna read out this R6 value because that's the top of the stack. I'm just gonna go right there. Okay, and you can see here's the arguments that are pushed. So hopefully right here, I'm gonna get this multiplied by this. So I think 1 by 5 times 5 by 1. If I click run, so I get 35. Looks right to me. It's 5 plus 8 plus 9 plus 8 plus 5. Yeah, I think that's 35. And let's try some different example. Maybe add some negative numbers. let's just try. I don't know. 5, 4, 3, 2, 1. We can try 1, 2, 3, 4, 5 again. Okay. Oh, forgot. Sorry. Forgot to actually click on subroutine. It says MatrixMult. 2, 3, 4, 5. 1, 2, 3, 4, 5. Some random numbers. I don't know. Click run. I get 15. Someone else could fact check that. That looks right to me though. Like 20. It's 25 minus 16 plus 3. Yeah, that looks right. Anyway, yeah. Hope this is cool, and hope this helped for time lab 3. I know homework's already due, but at least I just hope it'll help for time lab 3. I guess. Yeah. Thanks for watching.